Welcome to Biology of Marine Mammals. I'm Dr. Leslie Williams, and this is the second part of looking at life in an aqueous environment. In this lecture, we're going to explore the final property of water. That is that water transfers heat 25 times more efficiently than air does. So the first thing we'll do is we'll explore that property, and then we'll take a look at several adaptations, including adaptations for insulation and how shape actually helps to minimize that heat loss. Okay, so water transfers heat about 25 times more efficiently than air. The first thing we'll do is we'll say, why does this matter? Why is this an important property? Now, remember that most of the animals on Earth actually came from the water, so there's tons of fish in the water, but there's actually very few mammals in the water. And unlike fish, mammals are warm-blooded. So here's what that really means. Mammals have to keep their temperature at a certain point, and it's pretty warm. To do that, they actually use metabolism, which is a collection of chemical reactions. So when you take a look at the total volume of a given mammal, you can imagine that there's all of these little cells in there that are important in generating the heat needed. Now, mammals are constantly trying to keep their heat so that they don't get too cold. If they get too cold, their whole body function starts to fall apart, and that is what we call hypothermia. Humans are, of course, subject to hypothermia. In fact, you might already have anticipated that water, of course, makes hypothermia much more likely. You take a human, you put them in 70 degrees Fahrenheit air, they can live there for 3 days, no problem. You put them in 70 degrees water, too much heat gets drawn away and they die from hypothermia, even though the water doesn't seem to be that different than the air. So, because marine mammals are, of course, mammals, also warm-blooded, they have to keep their temperature nice and high and consistently high. They are constantly struggling with the fact that water is actually going to draw away the heat 25 times faster than air will. In other words, they lose much more heat than we do. So, many of their adaptations are designed to specifically cope with this continual challenge so they don't freeze to death in their environment. Okay, so the adaptations to deal with this continual heat loss really come in two forms. The first one is to improve the insulation. If you've ever had a house that possibly gets very cool, of course, one of the ways you can keep the heat in is to add extra insulation in the walls. Why not do that for a body as well? So there's two ways that mammals in general do this, one of which is called blubber and the other is fur. We'll take a look at both of them in just a little bit. The second adaptation actually has to do with your generic shape. So one of the ways that we can reduce heat loss is by actually changing the surface to volume ratios so that we have less surface area for the volume of the given body. So this actually has a couple different answers. One is to have a more spherical shape, and the other is to reduce the number of appendages. Of course, these are appendages, these are appendages, this is an appendage. Reduce the number of those that are big areas where a lot of heat gets drawn away. And of course, again, if you've ever had frostbite, frostbite happens on your appendages, your fingers, your toes, your nose, and your ears, and this is because there's not a lot of heat production in that area, but there's a lot of heat loss in those areas. Okay, so let's go ahead and take a look at one of the first solutions in insulation, which is blubber. So in order to answer, well, what is blubber? Let's take a look at the skin, because blubber is actually a part of the skin. So when you take your skin, and you guys can do this, you can go ahead and pinch your skin like this and move it around. You'll notice that your skin doesn't actually come off totally, but you can definitely pull it up from the underlying muscle. The skin itself actually has 3 different layers. The epidermis, the word epi always means on the top, the actual dermis, which is the skin, and then a layer directly underneath that that forms that barrier between your skin and the underlying tissue. That is called the hypodermis. Here on this model, we can see kind of a bigger picture. The epidermis is actually just the top layer. It's what flakes away day after day. And when people say you lose millions of skin cells, they're talking about that. And then, of course, the dermis is going to be this area right here. You can see the hair bulbs are embedded in there. There's blood in there. If you cut down to your dermis, it will bleed. But then there's this area down here that's called the hypodermis. And the hypodermis is actually full of fat. This is where you store a lot of your fat. Now, we have a layer of fat in our hypodermis no matter where it is, but of course that thickness varies depending on where you are. Around like your fingers and your eyelids, there's very little hypodermis, very little fat, but you go to other areas of your body where people tend to store a little bit more adipose. Of course, the hypodermis is going to be a little thicker there because there's more fat storage. But as a rule, if we take a look at a human, you might say the hypodermis on average, maybe in an area like the arm, maybe a couple millimeters thick, which is really small, very, very small. You go to a marine mammal, their hypodermis might be like this, very thick, almost half a meter in some cases. That's a very thick hypodermis layer. So we give a special name to that. It's called blubber. So blubber is actually going to be a hypodermis that is thickened by adding extra adipose or fat. Fat is a great insulator, and it's used primarily for insulation. All right, so just to reiterate a couple differences in the hypodermis between most terrestrial mammals and marine mammals. Remember, terrestrial mammals are not experiencing the same forces that marine mammals are. Terrestrial mammals are in the air. We don't lose a lot of heat, therefore we don't need a huge amount of insulation. So as a rule, our hypodermis is pretty thin. But when we get to the marine environment, we get much, much, much thicker. And here's a picture of a Weddell seal, and you can see its blubber layer is massive. In fact, it looks very, very, very comfortable lolling around there on the ice floe with its major blubber layer, where we, if we were to actually go out there, would be freezing because our hypodermis is so thin. Okay, so that's not the only insulation strategy, although it's certainly one that's used especially by phocids, which of course are your true seals, and then by most cetaceans, so those are your whales and your dolphins. But some marine mammals, especially those that we call amphibious. Now, amphibious means that they spend some time on land and some time on water, in the water. Those amphibious marine mammals, they tend not to have as thick of a blubber layer, and so they use a more standard form of insulation, and that is fur. Fur, of course, is a hallmark of mammals. All mammals have fur, including us. We have fur. We even have it all over our body, even though it's not very thick. So this is hair. Of course, so many otariids, including the fur seals, which is how they get their name, the polar bears, and then also the sea otters, use more of their fur for insulation rather than their blubber. So when you take a look at these pictures, you'll notice that at least in the upper picture here with the sea lion, the fur seal, they don't have nearly the thick blubber layers that we saw in that Weddell seal that was laying on the ice floe. Much thinner layers, but instead they use fur. Now, of course, with man's takeover of the world and constant interaction with marine mammals, this has posed a huge problem, and that has to do with oil spills. So probably one of the poster marine mammals for oil spills is indeed sea otters. Sea otters are at great risk every time that we have an oil spill in the vicinity of a sea otter colony. And that is because sea otters have a very thin layer of blubber. They do not use blubber much for insulation, but they have a very thick coat of fur. In fact, they have the densest fur coat of any mammal on the planet. So what happens is when we have an oil spill, the oil coats that fur and basically shuts that fur. The way fur normally works in the water is it keeps an underlying pocket of air close to you, similar to the way a down comforter works. When you wrap a down comforter around you, it's nice and warm because it traps air, and the air is actually what keeps you warm. So when the oil sits there on that fur for the sea otters, they can't trap air under, and their fur loses its major insulating property, and they freeze to death. So when sea otters die of oil spills, it's almost always because they actually freeze to death from lack of that insulation. All right, now that we've looked at that one, let's go ahead and move to the second adaptation, which is taking a look at shape. So shape absolutely matters in heat loss, and this is because wherever you put your surface, your skin, next to water, you're going to lose heat. So to lower the amount of heat loss, you want to expose as little skin as possible to the water. In order to do that, you want to have something that has a large volume but a low surface area. The best shape to do this with, which has the lowest surface area to volume ratio, is actually a sphere. And I have up here some calculations. You don't have to do these calculations, but I certainly want you to look at the overall numbers. This is a sphere with a volume of 4. I've picked a radius of 1, it makes a volume of 4. But the surface area, that's of course the skin that coats that sphere, is going to be a little over 12. So that gives our surface area to volume ratio about 3. In other words, there's 3 times as much surface area relative to the volume. Now let's take a look at a cube that has the exact same volume. So again, a volume of 4, same volume, which means same heat generating capacity. Surface area is a little bit larger, 19. When you take 19 and divide it by 4, you get 4.75. So this one has a larger surface area to volume ratio. So the net take-home message here is that if you thought that these were both animals, and I'm going to go ahead and actually take a look here. If this sphere was an animal and this cube was also an animal and they are the same volume, this cube is going to lose about 50% more heat than this sphere does. In other words, if you threw them both into the water and they died of hypothermia, this guy would die faster than this guy would, only because this guy is losing a lot more heat compared to the cube. Okay, so certainly having a more spherical shape, as we've just determined, is going to be advantageous to retaining your heat. But there's another thing as well, and that is to reduce the number of appendages. So if we take a look at this cube and we say, okay, here's the wrappings of the cube. If you wanted to wrap this up with tinfoil, this is how you'd go ahead and wrap it. We're going to go ahead and add appendages to this cube. We haven't changed the volume much, but we've certainly changed the surface area. All of these thin appendages require lots and lots of wrapping. So by having more appendages, we lose much more heat. Okay, so again, the general trend is that marine mammals, at least ones that are obligate or they need to be in water all of their life, want to have a more spherical shape and they want to have small appendages. So there is a pressure to become more spherical and have smaller appendages to reduce heat loss. All right, the very last thing to look at is this idea of getting big. Now, another way to lower the surface area to volume ratio, which is advantageous, is to get really big. And again, we can quickly go through the math here and see if we double our volume, even keeping the same sphere, we actually lower our surface area to volume ratio again. So 2 major adaptations: be spherical, have fewer appendages, and then get big. Big is good. So of course we see big marine mammals all of the time. Last take-home point here is the idea that animals that do not spend their time in water solely, they're amphibious, may need to keep their appendages for mobility on land. So they may be pulled in 2 different directions, and so you'll see a lot more large appendages with those marine mammals because they need to move. Thank you.